So our speaker today is Makoto Yamashita, and his title, as you can see there, is Chern character for torsion-free ample groupoids. Please, Makoto, go ahead.
Yeah, so thank you very much again for invitation. And so I'd like to report my recent paper with Valerio Proietti, who is doing postdoc with me in Oslo. And so we have been working on related topics since beginning of pandemic, so since 2019 or so. But yes, so in our most recent paper, we managed to prove something that could be interpreted as Chern character map for C-star algebras of certain groupoids that you will see more in detail. So, oops. Yeah, so the plan is to compare two sort of homological invariants for groupoids. And so let me start with the first invariant. So starting from topological groupoid, so that encodes dynamical systems, so meaning space and some transforms, collection of transforms. And in sort of baby examples, they come from maybe groups acting on topological spaces. Or a bit more involved example is hyperbolic dynamics on some metric space called Smell space. The structure itself is given by a compact metric space and certain homomorphism, self-homomorphism with hyperbolicity. But then starting from that setting, you can look at expanding directions or contracting directions, and then you get very interesting groupoids. So those were original motivations for us, but it could be quite flexible. So starting from any topological groupoid, then you can go into two directions. One is more homological and another is more analytic, maybe. In the homological direction, what you want to do is to look at the space of composable tuples of elements in the groupoid. So that means technically they are called knobs of the groupoid. So you just look at the n tuples of elements like G1 up to Gn that are composable. And then if you look at all these spaces for different n's, they are related in very nice ways. For example, if you take concatenations of two consecutive elements like G1, G2, or G2, G3, then you decrease n by 1. Or if you insert identity somewhere, then you increase n by 1. You get a simplicial topological space this way. And of course, this is already quite nice, but what Crainic and Moerdijk worked out is if the groupoid is étale, that means structure maps like source map and range map from arrow space to the base space, local homomorphisms, then you can define very nice theory of homology, with possibly with some coefficients given by equivalent sheaves on the base space. Anyhow, it's a very interesting homology theory. So in the space direction, this is more like compact support homology. But in the arrow direction, this is really like group homology in a way. So you really mix compact support homology and homology in very intricate way through this simplicial space of nerves. That's the homology algebra side. And on the analytic side, so there's more sort of usual stuff you see in non-commutative geometry. What you do is to look at the functions on the groupoid and then linearize product on G. That means look at the convolution product on functions. And then you get some operator algebra, to be precise, C-star algebra. And once you have a C-star algebra, then you can look at invariants like topological K group of the Banach algebra. So there are two K0 and K1 of this groupoid algebra. And also there are more sort of, intricate background structures encoding maps acting on these topological K groups. And then so, these topological K groups or natural maps encode computations like eigenspaces of some operators in the groupoid algebra, or maybe Fredholm index for certain Fredholm operators in the algebra. And then, so these two parallel theories are perfectly like fine, and they give you many interesting computations. But can you relate these two? I mean, so a priori they look very different. I mean, if you look at the ways they are defined. But so this connection is what I want to talk today. And the summary of main result goes as follows. So the setting is the ample groupoid. So that means, I mean, so there's quite a lot of adjectives: Hausdorff, locally compact, totally disconnected, and second countable to be precise. And so these are basically totally disconnected groupoid with nice topology. And then it's also étale groupoid, meaning that the range and source maps are local homomorphisms. Then one thing you can do is to look at the C-star algebra. So that's the look at the compactly supported continuous functions on G and look at the convolution product. So linearization of groupoid product. Then you take the certain C-star algebra closure. This is the analytic side. And on the homology side, it goes like this. So because of G being totally disconnected, actually things get a bit easier than the general topological groupoid. So in the space direction, you don't really have to do anything. So you just take the compactly supported functions into rational numbers, say. So that's just the linear combination of characteristic functions for compact open sets. Then the nice thing is if you have local homomorphisms between, say, totally disconnected spaces, then you get summation over fibers. So this is the, it's not the Pruback functions, but you really just sum functions over fibers. Then if you look at the simplicial system of totally disconnected spaces, G N, so the nav spaces of G, then you get some simplicial group this way. And our main result says with two more extra assumptions. The first one is a bit analytic, and it has something to do with Baum-Connes conjecture, the well-known conjecture for group C-star algebras. And there's a groupoid analog to that. So if we require that the G, this ample groupoid satisfies this analog of Baum-Connes conjecture, and then whatever it is. And the other thing is more sort of homological in a way. The stabilizers are torsion-free. So stabilizers just mean arrows from given point to itself for any x. So under these two assumptions, actually, we can say that the topological K-groups of the C-star algebra rationalized, isomorphic to groupoid homology. So this homology of the simplicial group, and up to sort of periodization of decrease. So you have to do this periodization. That means look at the degree I plus even integers for all possible n. So this is to be expected because K theory satisfies both periodicity. So you have to do this.
Couple of questions,
yeah.
if I may. So the groupoid homology does not need to vanish in high degrees, does it?
Yes, so of course, I mean, so this is like group homology with coefficient.
Yeah, well, I mean whether the sum and the product are different.
Yes, so good point. So this could be all non-trivial for all higher ends. I mean, in principle, yes, yeah. But of course, for interesting examples, you have finite nest integrity.
Okay, so yeah, and so what you're saying is that the left-hand side of Baum-Connes is the sum.
Sorry, say again?
The left-hand side of Baum-Connes The Baum-Connes
Yes, yeah.
conjecture,
So
yeah.
of course, I mean, so this is in a way closely related, and so I will
Okay.
get that so that comparison.
Okay.
But
Okay.
yeah, in the end, so somehow one thing, maybe one major thing we have to do is originally the Baum-Connes conjecture was defined a bit more geometrically. So the left-hand side of Baum-Connes had all these geometric informations like spin structures on manifolds acted by groups and all that, and de-geometrify everything and do completely algebraic approach to that. So that's one of sort of recurring thing for our work. Yeah, but still, I mean, so it's a computation is very much motivated.
So your computation, I mean, for discrete groups, this was known.
Yes, so this is also, I mean,
this is
one thing
generalization.
maybe I should mention. So this probably comes in like the bottom half of this page. So bear with me. So the model case or toy case maybe is the case of transformation groupoids. So starting from say group acting on space, then you can define what's called transformation groupoids. So the underlying set is underlying arrow set is just the Cartesian product of group and the space, and then you define multiplication according to this law. So in other words, so, if you say this is y, say gamma comma y product gamma prime x, that's defined on if and only if gamma prime x is y. And then, yeah, so I guess this is probably answering your question, comment. So, I mean, so in this setting, what we do is known actually since quite early days of this K-theory with groups acting on C-star algebras. So I think the early, I mean, of course, the probably earliest sort of result in this direction is Pim's-Navier sequence of group Z acting on C-star algebras, and then you get something like invariance co-invariance computation for the natural induced action on the K group of coefficient. But Kasparov did it very something very general and also closely related to what we do, at least in like Crain. So he showed that in his paper about equivariant KK theory and Novikov conjecture, he showed that if gamma, if classifying space B gamma has nice geometric model, then you get a spectral sequence of group homology with coefficient. Coefficient is the K group of the function algebra on the space X. I mean, in his formulation, actually, instead of C0X, it could be any C-star algebra acted by gamma, but adapted to our setting, it becomes like this. And there's a spectral sequence with E2 page as this group homology, and the limit is the topological K group of the groupoid C-star algebra. And I mean, a priori, so this is only a spectral sequence. So you have to see like if it's degenerate up to torsion or how it could be non-trivial. And of course, the Baum-Connes conjecture. So this is in a way very nice sort of packaging of this kind of computation that gives at least systematically a map from this equivariant K homology group of the universal gamma space to topological K group of the groupoid C-star algebra again. And if gamma satisfies Baum-Connes conjecture with coefficients, or maybe a bit more generally, if gamma cross X, this transformation groupoid satisfies Baum-Connes conjecture, then this map is isomorphism. And also, in more modern approach to Baum-Connes conjecture due to Davis and Luke, so this left-hand side of Baum-Connes conjecture could be interpreted as extraordinary equivalent homology for gamma. And the crucial point is if you have extraordinary homology and rationalize it, then you get ordinary homology. So that corresponds to more or less spectra. That's if you have a spectrum and rationalize it, then you get module over the Eilenberg-Maclaurin spectrum. Then it has to be also Eilenberg-Maclaurin spectrum. So with this kind of homotopy algebra argument, actually you get ordinary homology after rationalization. So this is really useful and powerful principle, I think. So that's why in our theorem we have to rationalize also. Otherwise, so this, for example, even in this transformation groupoid case, so this Kasparov spectral sequence could be non-degenerate, but the claim is only non-degeneracy. So only subtlety in higher differentials are in torsion.
So is that so? Are you saying that this is a general fact about homology theories, that the spectral sequence always degenerates rationally?
Yeah. Yes. So I think that's what I am saying. Yeah.
Okay.
Very formally, and so if you have a functor from so I think sorry, so I need to be a bit careful with what I am saying. So so I think I am oversimplifying some of the stuff. So for example, so this is equivariant homology still. I mean, so there is extraordinary part and equivariant part, and rationalization takes care of extraordinary and makes it ordinary. But still, there is equivariant homology versus group homology. And in general, if X is a non-trivial, if X is not totally disconnected, then you have spectral sequence starting from group homology to, and then abutting to equivariant homology. And so this could be still non-trivial. But if X has dimension 0, totally disconnected, then so this self-spectral sequence is again degenerate. So there are sort of two steps, of sort of two things to take care. And for totally disconnected space, you don't have to worry about this self-spectral sequence. And after rationalization, extraordinary becomes ordinary. So there are two sort of things to sort of working independently.
Okay, thanks.
Yeah. And then, of course, I mean, we have quite a lot of assumptions, like G has to be totally disconnected or have torsion-free stabilizers. And so there are things that are easy to relax and difficult to relax, I think. For example, G being étale groupoid, so the structure maps being local homomorphisms. So this is a bit difficult to remove because so the groupoid homology is defined only for étale groupoids. And at the end of the day, we have to work with this sort of summation over fibers, and that really requires this étaleness of the groupoid. And also this Baum-Connes conjecture for groupoid, this is basically impossible to remove, or else we would be computing left-hand side of the Baum-Connes conjecture, whatever it is in the groupoid setting. So these are sort of there. But then the other things, I think, could be relaxed. For example, groupoid being totally disconnected. To remove that, then you have to encode this compactly supported cohomology in the space direction. And so this is what we are working on right now with Valerio. And so I think we have some ideas to do homotopy algebra, homotopical algebra, right, in the right way to encode this. And also torsion freeness of the stabilizer. So this is for the case of groups or transformation groupoid, people know what to do. And so you have to do Proudhon homology for groups. And in joint work with in progress with Christian Bunke, Ali Miller, and Valerio, and Christian Voigt, so we are working on this groupoid version of Proudhon homology. And so I think so we also, in due time, we have the right model Bourdon homology, and then so that would give you computation of say
sorry, would this groupoid equivariant homology, would this be a factor on so if I have a groupoid G, would this be on the category of this give a homology theory on the category of G spaces?
Yes, I mean, so this is a bit difficult to directly translate. So the category we have is the category of open proper subgroupoids of G, and then
so the orbit category.
Yeah. So instead of the homogeneous space, we have to work with subgroupoids directly. For the case of groups, you can go back and forth, but for groupoids, the thing is, for example, subgroupoids acting on the bigger groupoid might not be proper. So this natural translation action might not be proper. So it's better to stick to subgroupoids rather than homogeneous spaces. But so up to this kind of sort of standard.
But I mean, in the group case, it is equivalent to work with functors on the orbit category. And to work with G spaces.
Yes. So you can.
What I'm asking is the G space part, not the. I know how to modify the orbit side. I meant the equivalence with G space. So does this work, you say?
Yes. So the like I said, actually, it's already difficult to work with orbits. So instead of orbits, we have to work with subgroupoids. It's a bit difficult to go into that direction, I think. And finally, so there's also instead of the groupoid itself, or like C-star algebra groupoid, so, it's also natural to consider cross-product C-star algebras when G acts on other C-star algebras. Then again, I mean, so you want to compute topological K group of the cross product, or this groupoid homology with coefficients coming from the K group of the algebra acted by G. So this is also natural. And to be honest, so this one, we need a bit more of the homology algebra with sheaves. And again, the problem is to sort of incorporate algebraic topology that takes care of all these homotopy constructions like geometric realization and all that with more of sheaf theory. And so this one, maybe we need some ideas. But at least at the level of homology algebra, we know what to do. Okay, so let me quickly go over what we mean by groupoid actions on spaces and algebras. So or maybe in the interest of time, so let me be a bit brief. So when we say that the G acts on space, that means there's an anchor map into the base of the groupoid from that space acted by G, and there's a natural action map. But anyhow, so this is really very standard thing. So we don't really have any new inputs here. So, and for C-star algebras, so you have to theorize this action on space into the language of algebras of functions. And then, so there's a natural generalization to C-star algebras. Then formally, you want to make sense of f times a for f function on the base of groupoid and a in the algebra acted by groupoid. And that should sort of make sense in a consistent way. So among other things, fa should be equal to af. And also there should be natural action map. And for us, for this talk, in the end, the spaces we are interested in are the nerves of groupoids, and algebras would be functions on the nerves. All right, then so there is a homology algebra of such things like spaces or algebras acted by the groupoid G, and this has quite long history since early 90s. So first, Gall defined analog of Kasparov's equivalent KK groups for groupoids, and to be precise, locally compact Hausdorff groupoids. And then, if you have separable C-star algebras acted by such G, then one can define these equivalent KK groups, KKG of these two algebras. And he showed that these groups give you additive category. So that means there's a product that acts as that serves as the composition of morphisms in additive category. And then after Meyer and Nest approach to Baum-Connes conjecture through triangulated categories, and also for the technical result due to Oyono and Tu for this KKG, this Gall's KK theory, then we showed that this category is triangulated. But then the idea is really following Meyer and Nest work. So the suspension is given by C-star algebra suspension. So maybe it's better to call this more like the path space, because I mean it sort of looks like path space also. But whatever you call it, it's given by functions from open interval 0, 1 to the coefficient algebra A that vanishes at both endpoints 0 and 1. And exact triangles are mapping cones. So that means if F is a homomorphism from A to B, then you can construct something called mapping cone. So that's given by tuples, pairs A and G. A is in the domain algebra A, and G is a function from half open interval to B, and with this consistency condition. Okay, then the suspension of B embeds into this cone algebra naturally by taking just 0 in the first component and inclusion in the second component. So what's hidden under the carpet is any KK morphism can be represented as an equivalent homomorphism. So that follows from Oyono's computation. And also in our previous work, in our first paper with Valerio, we showed that the simplicial system of these G algebras coming from the nerve, so they form a kind of projective resolution of the functions on the base, following the scheme of Meyer and Nest. And so that gives you things like spectral sequence, whose E1 page is the functions on the nerves, or a bit more conceptually, cross product of these nerves whose degree is shifted by 1 with G acting. Because what is resolving the base is these nerves with degree shift. And if you look at what the E1 differential is, E2 page is on the nose groupoid homology with integer coefficient. But so this is all like homology algebra for better or worse. And then to understand the degeneration of these higher differentials after rationalization, we have to do homotopy algebra, because we really have to understand spectra behind this computation. And the first step is to understand the Dwyer-Kan localization of the category of G-C-star algebras. And here we follow recent approach due to Bunke and his collaborators on Baum-Connes conjecture for groups. So, the crucial point is to try to find infinite category behind this triangulated category KKG. And then infinite category allows more natural gluing operations that's difficult to implement or compare in triangulated category. So the thing is, in a triangulated category, if you have a simplicial system and if you have two simplicial systems, for example, and try to compare them, then there is something called higher order brackets that you have to take care all the time, and this is impossible to compute, I think. But if you have infinite category, then you can so compare different simplicial systems more naturally. So anyhow, the theorem, intermediate theorem we have is, if you look at the infinite categorical localization of GC star algebras by the KK equivalent homomorphisms. So usual localization just gives you another category where you force all these distinguished morphisms to be invertible. But here, this is Dwyer-Kan localization. So it's a infinite category presented by, for example, simplicially enriched category. And then how do we get stability? I mean, so defining infinite category, this is something you can always do. But then you have to show that this is a stable category. So that means, for example, the homology category is triangulated. Of course, it should be KKG. And also there should be finite limits, colimits, and all that. And so here you want to recognize the background categorical structure as a category of fibrant objects. So there's no way to put model category structure on the category of GC star algebras. But category of fibrant objects, so due to Brown, this is much more flexible, I mean, much more general, and it does apply to the category of C star algebras. So there, you don't have to define collaborations. You need to only specify fibrations. And here we say that the equivariant homomorphism is a fibration when there is a splitting map. And this looks a bit technical, but you want something called complete positivity to play nice with KK theory. And so if you only ask for example, F being surjective, this is also compatible, and you get another category of fibrant objects. But that would correspond to E theory, and we want to do KK theory, so we have to do this. Anyhow, of course, you need to check some compatibility for purpacks, but that's very standard. And then you get category of fibrant objects in Brown's sense. And there's one extra condition that you can find in Chinsley's recent book. And so that's also very natural. So any morphism can be factorized as weak equivalence, then fibration. And so the correction F and W satisfy this extra assumption. So that implies that the Dwyer-Kan localization is actually a stable infinite category. And countable direct sums, that's a feature of KKG. So you can see that the countable direct sum of C star algebras is a model for countable direct sum. And like I said, so we model this on the by Bunke, Engel, and Hunt. And yeah, and also in the trivial case, if the groupoid is trivial, then this is much order due to random Nicholas. Okay. So yeah, so that's the sort of homology algebra background, and we want to use this to compute this homology algebra approximation that we got before. And then what we have is the simplicial system of nerves. So say G n plus 1 tuples of composable arrows, and étale maps as structure maps. So we have to use concatenations as structure maps. So they don't quite give you homomorphisms of C star algebras, but only something like what you should think is what is called Atiyah transfer sometimes. And concretely, what Atiyah proved was if you have a finite covering map of compact spaces, then you have this transfer map. So usually what you have is, if you have a continuous map of, say, compact spaces, then you have sort of cohomological contravariant functor map, but this is covariant. And again, it's really summation over fibers in a way. And a bit more conceptually, we should look at the spans. I mean, one thing is you have to get rid of compactness because these groupoids and nerves are not compact. So you should look at things like proper spaces and also instead of proper maps, and also instead of finite covering maps, work with étale maps, local homomorphisms. Then you expect the spans, so Z mapping to X by proper map and mapping to Y by étale map to give you a morphism from C0X to C0Y in the Dwyer-Kan localization. And then there's a very useful intermediate category, or more like 2-1 category to be precise, of C-star algebras and proper correspondences. So if you have such span, then you get something called proper correspondence. So that means you get the Hilbert module over the target algebra C0Y. I mean, what you take is some completion of compactly supported functions on Z, intermediate span space. So there you get action of C0Y and then also C0Y valued in the product. Then the nice thing is the map from Z to X is proper. So that means natural action of C0X is by compact endomorphisms. And so here you have a very straightforward map from the category of spans to the category of correspondences. And then what we showed was there's an infinite factor from this 2-1 category of equivariant proper correspondences to the Dwyer-Kan localization of C-star algebras. And so we did it by hand, like really constructing, looking at the concrete implementation of this Dwyer-Kan localization as simplicially enriched category coming from hammock localization and then X construction applied to morphism space. So you have to sort of enrich the morphism space this way and then directly construct 2-1 factor out of the dusting nerve of this 2-1 category. But more recently, actually, Ralph Meyer published a very nice short paper that gives you interpretation of these proper correspondences as certain Dwyer-Kan localization of C-star algebras for much smaller class of equivalences. So you just look at something like corner embeddings instead of all KK equivalences. And then you get proper correspondences as Dwyer-Kan localization. And because these corner embeddings are obviously KK equivalences, you can use universality of localization and have this kind of functor. So one way or another, you get this. All right. Then, so with this, you get a simplicial system of functions on the nerves. And once you have a simplicial system, then you can make sense of the geometric realization. Formally, it's a infinity-categorical colimit of this system as a functor from the simplicial category delta up into our stable infinite category of GC star algebras. Then, so this is really doing the right thing, meaning that the this cross product of this colimit by G. So that's really left-hand side of Baum-Connes conjecture. And there is a natural map from this colimit to C0X, C0 of the base of the G. And so that's the model of assembly map. So this way you can make these Baum-Connes conjecture for groupoid completely non-geometric and purely algebraic. And also, this cross product by G is compatible with colimit. So you can do cross product first and then take colimit. So this way, you are looking at the simplicial system of these transformation groupoids, but G acting on the nerves. So there are free actions, proper and free actions. So you can take the quotient and then reduce the degree of the nerve by 1. Then we are looking at this colimit of simplicial system of functions of nerve instead of cross products. Right? And another ingredient is enrichment of morphisms by spectra for stable in categories. So this is again very general thing. Then you can take the map space or maybe map spectra, and then that says if you look at the these map spectra for these algebras going into P cross G, then they would approximate map spectrum of C star G here. Okay. So this is the homotopy algebra implementation of assembly map. Then, well, I mean, so that's maybe nice, but the price to pay is, of course, this left-hand side of Baum-Connes conjecture is only given as some simplicial system of spectra. And we have to extract something computable, like that would give you groupoid homology in the end, right? So that means starting from this simplicial system of spectra, that would at best give you extraordinary homology to something giving you ordinary homology. And here, the first step is to extract more like concrete spaces, like really topological spaces, instead of some simplicial set representing, say, map spectrum in stable in category. And so here, the crucial thing is Karubi's old work solving something called Atiyah-Singer conjecture that says the Ku spectrum, like the CW spectrum that you can find in many places, built out of the classifying space for unitary group. So that's really classifying sort of spectrum for K theory. So meaning, if you want to compute this sort of spectrum version of map space for the usual K theory of C star algebra, this is weakly equivalent to the map space of X one-point compactified mapping into Ku as based space. Of course, I mean, Karubi didn't state it in this way, but it's something you can extract from his work. Okay, and so so for each n, so this says that the so this spectrum is actually some map spectrum from nav to Ku. But we also have to understand what the structure map of simplicial system is. So there we have to understand the functority for spans. Like in the end, we want to understand étale maps. So and then what we proved is that if you look at the 2-1 category of such spans, then they are actually classified by the value at singleton space. Of course, you want to assume some consistencies, and the crucial consistency is if you are totally disconnected space, that would be in the Gn, is presented as projective limit of some finite sets or maybe discrete spaces, then the value of f should be computed as corresponding colimit, I think, because so this would be the projective system of proper maps, and so you apply this kind of compatibility for proper maps. Yeah. And so of course, there's a model result. If you instead work with discrete spaces, so just sets or maybe finite sets, then this is well known. I mean, so if you look at the span category of finite sets, so this is infinite category with sort of product and sums being equal, and it's a semi-additive infinite category, and it's a singly generated inverse to one category. And what we are asking is add totally disconnected spaces, but knowing that there are always projective limits of discrete sets. So if you ask for this consistency, then you still have the same kind of classification. Okay, then why does it help? So we can say that the really as a functor from to one category of spans. So this map space construction, map spectrum construction with Atiyah transfer to one infinite categorical model Atiyah transfer is the same thing as map space construction into KU with the transfer structure given by this kind of classification. So they are equivalent. And for totally disconnected spaces, I mean, once you have things like Eilenberg-MacLane spectra as the value, then you can instead work with actual simplicial groups of compactly supported function from X to coefficient like 2. And why does this lead to ordinary homology? That's because after you rationalize everything, then you can just rationalize the coefficient. So that's Ku rationalized. But so this is really the usual spectrum computation that gives you H2, Eilenberg-MacLane spectrum of 2 with degree shift. Again, because of pot periodicity, you always have to sort of add even degree shift all the time. But yeah, so it's really some concrete Eilenberg-MacLane spectrum of graded group. Q with Laurent polynomial in formal variable of degree 2.
So, sorry, your vocabulary is that, so when you say that the homology theory is extraordinary, you mean that the spectrum corresponding to the point is not just some of Eilenberg-MacLane spectrum.
Yeah, so yeah, exactly, yeah.
Because if I mean, according to the Wikipedia,
yes,
extraordinary means that when you evaluate at the point, it's non-zero, not that it is.
Okay, yeah, sorry, yeah,
so,
maybe
okay.
yeah, so I really mean in the sense you first said. Yeah, sorry, maybe I shouldn't say this. I really mean so either like something
thanks.
that's given by maybe yeah, sorry, so I think I picked it up from some book by maybe Adams. Yeah, so I mean that. And then so you really want to go to Eilenberg-MacLane spectra so that's only happening after rationalization. So yeah, so I think sorry, so I think I went a bit too fast, but anyhow, so this is the summary of what's happening. So we have after rationalization, we have this simplicial system of map spectra from this NAV mapping into the Eilenberg-MacLane spectrum of this Laurent polynomial. And then if you compute the homotopy group, I mean, so it's because you can replace this map spectrum by again Eilenberg-MacLane spectrum of GN compactly supported functions on the nerves with coefficient in this Laurent polynomial. So you get groupoid homology. That's very standard, I'd say. And this geometric realization is isomorphic to the map spectrum of in the KK category of between complex numbers and groupoid C-star algebra. And after taking fundamental group, after taking homotopy group, you get topological K group of the C-star algebra. So this way you get the comparison. Yeah, so I think I am done with what I prepared. So yeah, thank you for your attention.
Okay, thank you very much for your talk. I suppose you are aware, so there is in the group case, so you have discrete groups, right?
Yeah.
So the computation of the left-hand side of Baum-Connes, rational computation of left-hand side of Baum-Connes, and of Fadel-Jones, there is some paper by Wolfgang Luke in the Krell journal of 2002. Which, of course, it's a much easier setting because you just have these three groups, but it's more general. So do you aim to? I mean, are you aware of these results? And if you are, do you aim to try to show something similar for groupoids? Or do you think that would be true?
Well, I mean, so in the end, so the claims are going to be analogous, I think, and yeah, then so the so we have one thing. So maybe it's closer to the closest thing is the these two parts, I think. And like I said, with the trivial coefficient, I mean, if it's only a computation of K group for groupoid C-star algebra, then up to this modification of OB category into a category of some nice groupoids, open subgroupoids, then so I think so this goes very straightforwardly. But with the coefficient C-star algebra, then it gets a bit tricky. And of course, I'm definitely, for example, for homology algebra computation with triangulated category, then so this works without issue. And how to incorporate homotopy algebra into this computation. So this one, I am still struggling, but definitely, yeah. So I want to.
Okay. So are there more questions from the public?
Yeah, I have a question. So in your slide right at the end, don't you want to rationalize the K-theory side as well?
Yes, maybe. Oh, sorry. Yes. So thank you. Yes.
Yeah. And I mean, also, I propose that what sort of, I mean, do you expect the result to also go through without rationalizing?
No, I mean, so it's like trying to compare integral homology with topological K group for spaces, and I mean, so there are differences. So that I mean, of course, the interesting thing is like how much torsion you have to kill to have isomorphism. I mean, like rationalizing everything is maybe too much, but again, judging
but
from
I mean, don't you have the like in the space case, if you take the K theory of continuous functions, then don't you get the cohomology, like the sheaf cohomology of the space with coefficients in Ku?
Yeah, no. I mean, so maybe so you are thinking of Chern character isomorphism, and then so there are already like really nice manifolds, like some projective spaces, where you start to see the difference between integral cohomology and topological K group. And of course, the difference is only in the torsion part of the of the commutative groups. But yeah.
Right. I mean, but if I'm trying to compare K theory not with some form of singular cohomology, I'm trying to compare it with sheaf cohomology. And for that, I would just apply the results that you stated like 3 slides ago, where you can just take the functor which goes from compact Hausdorff spaces to spectra, taking a space to the K theory of continuous functions on the space. And that functor is determined by its value on the point. So then isn't the K theory just sheaf cohomology with compact support with coefficients with KU?
If you look at the conclusion of something like sorry, so I think I went.
I think one slide.
This one, right? So this one says you can classify such sort of homology theory by this value of singleton, but at best this is only a spectrum. So, and it's a bit different from, for example, is Atiyah-Hirtsev spectral sequence that says you can compute generalized cohomology by spectral sequence that starts from cohomology with sort of value at that point as coefficient. And so it's really either if you take coefficient in as commutative group or as a spectrum, I mean, so you really get this subtlety. So in that regard, so this one by itself doesn't really solve that issue.
Right. Maybe the other thing which is relevant to what I'm doing with Guido and Thomas Nikolaus, do you have a precise relationship between the cohomology of the quotient space of a group action, say on a locally compact space, and say the group action is proper? So one can talk about the cohomology of the quotient space, and then there's equivariant cohomology. Under what circumstances do these things agree? I mean, this is a general question, has nothing to do with it.
In general, I'm afraid it's difficult to say. For example, I mean, my favorite example is the computation for the Heisenberg group, and it's a how do I say? I mean, it's sort of 3-dimensional. So, but then, and also the classifying space. The universal proper action is just R3 because it corresponds to this 3-dimensional nilpotent tree group. And well, then so you can try to compute this using this central extension. So the center is just integer group and quotient is Z2, but the extension is non-trivial. And then if you look at this kind of action, then so in the end you have some things like BG, so this Heisenberg group being the fiber bundle with like base being 2 torus and fiber being circle, and I mean it's very concrete and simple. But then in the end you start to see difference between equivariant cohomology and cohomology associated to this extension. But it's very difficult to see if you don't do spectrum version of this. I mean, what I'm saying is, if you look at the cell spectral sequence or cell spectral sequence for this vibration, then higher differential is non-trivial, but that's really encoded by these things like homotopy action of the Z2 on the center.
Okay, thanks.
Are there any further questions from the audience? Otherwise, I'll stop the recording now.